Okay, now let's talk about our next method, which is the Newton's method. So the gradient descent method is the first order method. Why is that? Because we give it this name because we rely on the gradient to improve our solution. And as you know, gradient is basically first order derivatives. So first order methods, they are intuitive, but unfortunately sometimes they are too slow. First order method. So why is it too slow? There's actually no reason. It's simply because your function is nonlinear. Okay, so it's curved. It's weird, but you only look at its first order approximation. So that means you give up a lot of information that you may utilize to speed up your algorithm. So that's why some people would say, hey, how about we use second order method instead of first order? Or that means how about we take a look at our Hessian to see if we may rely on my Hessian to update to a solution, right? And the idea turns out to be the Newton's method. Okay, so before we introduce Newton's method for optimization, let's start from the Newton's method for solving a nonlinear equation, which may be similar, will be familiar for some of you. Maybe you have learned that in high school or some other courses. Okay, so what's that? Suppose I give you a function f, and I want you to find its root. So I want to find x bar such that f of x bar is 0. And to make the things intuitive, let's assume f is from R to R, so from R1 to R1. Okay, then what's the idea? Given any point x0, I first find its tangent line at f of x0. Okay, so I find its tangent line. And at the tangent line, the intersection of tangent line and the x-axis, I get the next solution. And then I do it again. I find another tangent line and the root of the tangent line, and so on and so on and so on. And hopefully, eventually, I will get to x bar. So that's the idea. So numerically, what should we do? For any solution xk, I first find the linear approximation of f at x bar at xk. So this fl is another function which is this line or this line depending on your xk. So what's that? This is that linear approximation which comes from your Taylor expansion of f at x bar at xk. Okay, so f of x is f of xk plus f prime at xk times x minus xk. And this is exactly your Taylor expansion, first order Taylor expansion of f at your current point xk. Now you have this equation. Following our idea, we should set the equation to 0, and the point that can make this equal to 0 is our xk plus 1. We will keep doing this iteration until the improvement or the modification of our solution is too small. So what do we mean by too small? Let's do some correction. We're going to check the difference between xk plus 1 and xk. Okay? If the difference is too small, that means we are not really modifying anything and we are very close to the solution. Okay, so here we don't have something like a gradient or a slope to check. Okay, you may even see that at an optimal solution, the slope is also not very informative. So that's why we use this condition to consider how much improvement we are getting. If we are getting too few modifications, then we stop. Okay, that's how we use slopes or the Newton's methods to solve a nonlinear equation. Okay, now it's time to do some optimization. So how do we do that? Suppose f is twice differentiable. We want to solve f by finding a global minimum, okay? Or if it's non-convex, then probably a local minimum is good enough. In any case, we are actually searching for a point which is stationary or whose first order condition is satisfied. So you see immediately why we want to talk about how to solve a nonlinear equation, because this is what we want to do, right? If we want to optimize f, then actually we are solving an equation with respect to f prime. Okay, so now everything follows. Given a point xk, what should I do? I want to find the linear approximation of f prime, and that would be f prime xk plus f prime prime of xk times x minus xk. Okay, and then what we want to do is to gradually approach x bar, which is our local or global minimum. So we will move from xk to xk plus 1 by trying to set xk plus 1 satisfying this equation. Okay, exactly what we did from the previous slides. And we will keep doing the iteration until we can see that following the previous idea, we will say, okay, until xk plus 1 and the xk are too close to each other. Okay, or here, because you are indeed doing optimization, so you can always check the the slope of your gradient, which is fine. Okay, so both are okay in this particular situation. Then you will stop if an optimal solution is found. Okay, note that f prime x bar actually does not guarantee a global minimum, as we mentioned. So that's why you may want to show that f is convex, which can be very useful. Okay, so that was the first interpretation of the Newton's method for solving a nonlinear program. Actually, we can also use another interpretation, which some people may think is more direct. So suppose I have a nonlinear function small f here. Okay, what we want to do is to find x bar which can satisfy the first order condition. So what I'm going to do is that given xk, I'm going to find a quadratic approximation of f at xk. What does that mean? Given xk, I want to approximate the function f with a quadratic function around the current solution xk. Okay, and if I want to do that, I need to use the second order Taylor expansion, which is this one, right? So given xk, I'm going to write down a function of x, which now is a quadratic function, as my quadratic approximation of f at xk. And then I'm going to solve that quadratic function by moving to the global minimum of the quadratic approximation. So that means given xk, my xk plus 1 is the optimal solution for the quadratic function. Okay, and that means I want to find x to solve, to minimize this quadratic approximation. Then let's see the connection. If I want to solve this problem, I need to differentiate this function with respect to x, right? So x is where? X is here, and x is here. Oh, sorry, there is a square here. So if I differentiate x, then I get this f prime. If I differentiate with respect to x here, then I get 2 cancel 1/2, and I get this thing. So I need this equality to hold. And if you turn back to one page before, this is exactly the equation we were talking about. Okay, so the two interpretations are somewhat different from different perspectives, but they are doing the same thing. If we do some arrangements, we can actually get this. What's this? This means your xk plus 1 can be obtained from xk by using this equation directly or formula. You need to give me x prime. That's the first order derivative. You also need to give me f prime prime, which is the second order derivative. And then give me the ratio. I'm going to give you xk plus 1. So that's the general idea of Newton's method. In the next video, I'm going to give you one example and then generalize it to n variables. Thank you.